Welcome to day 4 of the JNCIA Bootcamp. Today, we're diving into routing concepts in Junos OS. Whether you're new or experienced, this session will sharpen your understanding of how Juniper routers make forwarding decisions. What is routing? Let's take our home with its IP address of 192.168.1.1. It needs to send data to the coffee shop at 172.16.32.1. Routing determines the best path for the data. Routers, as we see here, router A and router B, use routing tables. In Junos OS, routing separates control and forwarding planes. Think of routing like planning the fastest route to a destination based on current traffic conditions. Routing versus forwarding. We have the control plane, which is like the brains of the outfit. It builds the routing tables. Then we have the forwarding plane, which could be known as the muscle of the unit. It uses forwarding tables to move packets. So we could say that the control plane is like your GPS calculating the route, while the forwarding plane is the car actually driving it. Junos routing tables. Below, we see the hierarchical routing table view. We see INET 0. That's for IPv4 unicast. We see INET 6. That's for IPv6 unicast. We see MPLS.0. That's for MPLS forwarding. And we see INET.2, which is used for multicast, and RSVP, which is reservation protocol. Understanding these tables is a key to mastering routing behavior in Junos. Route selection process. Here we have our LAN, and we also have our coffee shop with the IP address 192.168.1.1. We have 3 routes from the LAN to the coffee shop. We have our static route, which has a preference of 5. We have our OSPF route, which has a preference of 10, and we have an RIP route, which has a preference of 100. In Junos OS, when multiple routes to the same destination are available, the router must choose the best one. This process is called route selection. I wonder which one gets selected. How does it choose? Well, step 1, it looks at a route preference and compares them. Let's remind ourselves of our 3 routes. We have a static with a preference of 5, OSPF with a preference of 10, and RIP with a preference of 100. The first thing Junos looks at is the preference value, as we've already stated. Now, in this case, a lower preference means a higher priority. So in our example that we're showing here, the static route has the lowest preference, 5. So it wins over OSPF and RIP. Here we have 2 OSPF routes whose preference are the same. They are both 10. So if both preferences are the same, what happens next? If both preferences are the same, it moves to compare the metrics. The metrics in OSPF is the cost, and the lower cost is the better option. So in this case, our top route, or route A, has a cost of 10, and our bottom route, route B, has a cost of 20. So it will choose route A as the best route to the coffee shop. Installing the best route into the routing table. Once Junos selects the best route, it installs it into the routing table. Here we see the routing table. The route then gets copied into the forwarding table, where it's actually used to forward traffic. Only the best route makes it into the forwarding table. All others are kept in reserve. In the above routing table, we note that there are two routes to 192.168.1.1. One of them has a star next to it and one doesn't. The one with the star is the preferred route and is the one that will be installed into the forwarding table. Route installation reminder. Always remember, Junos uses preference first, then metrics. Static equals 5, OSPF equals 10, RIP equals 100, BGP equals 170. Remember, lower is always better. So from the above, static beats OSPF, OSPF beats RIP, RIP beats BGP, unless preferences are equal and metrics take over. Types of routes in Junos. We have a direct route. We have a local route. We have our static route. And we have our dynamic route. Junos classifies routes based on how they're learned or created. The main types, as we've mentioned, are direct, local, static and dynamic. So what we're going to do now is we're going to break each of them down. Direct routes. Here we see a router with an interface that has an IP address of 192.168.1.1/24. A packet is destined to 192.168.1.45. A direct route is added when an IP address is assigned to an interface. It tells Junos that the entire subnet is directly reachable through that interface. Local routes. Here we see our router and it has its own IP address, 192.168.1.1. This address is normally assigned to loopback 0. This IP is not for routing others' traffic, it's for the router itself. A local route represents the router's own IP address. It ensures traffic destined to the router itself is handled properly. For example, management access or ping responses. Static routes. Static routes are manually configured by administrators. Here we see router 1 and router 2. Router 1 has an interface with the IP address 192.168.1.1/24 and it connects to an interface on router 2 with the interface IP address of 192.168.1.2/24 on the same network. However, router 2 also has a secondary interface with an IP address of 172.32.1.1/24. For router 1 to know how to get to the 172.32.1.0 network on router 2, we can manually configure a static route, and this is how we do it. At the Junos CLI in configuration mode, we type set routing options static route 172.32.1.0/24 next hop 192.168.1.2. The next hop being the interface that router 1 does know about on router 2. Static routes are useful for simple or stable networks. However, they do not adapt if the network changes. Dynamic routes. Dynamic routes are learned automatically through routing protocols like OSPF with the OSPF hello packet, RIP with the RIP update packet, and BGP with the BGP advertisement. Dynamic protocols adapt to network changes and they scale better in larger environments. Let's recap the dynamic route types with a comparison table. So here we see our headers, which are route type, created by, adapts, and an example. Direct and local routes are automatic and based on interface IPs. Static routes are manual. Dynamic routes are learned from protocols and adjust changes in real time. Static route configuration. Let's recap our static route configuration again. As we can see above, we have router 1 and we have router 2. Router 1 has an interface with an IP address of 192.168.1.1/24. Router 2 has an interface with an IP address of 192.168.1.2/24. Those two IP addresses are in the same subnet. However, router 2 has another interface with the IP address of 172.168.1.1/24, which is not in the same subnet. As that IP address is in a different network, we need to put in a static route to that network so that router 1 knows where to go and which next hop to use. So let's go ahead and put that into the CLI. We use set routing-options static route 172.32.1.0/24 next-hop 192.168.1.2. In Junos, you configure static routes under the routing options static hierarchy. You specify the destination network and the next hop IP address. The next hop statement in the command tells router 1 that to reach the network 172.32.1.0/24, you need to send packets to 192.168.1.2. Reject and discard routes. Static routes can also use the reject or discard options. When a packet hits the route and is rejected, an ICMP error is shown. If we use a discard route, the packet is silently dropped. In other words, there is no response seen. As mentioned, reject sends an ICMP unreachable message, while discard silently drops the traffic. These are often used in aggregation or security. Default route. We can also configure a default route using 0.0.0.0/0. Now what this means is if no other route matches, use this path. It's commonly used to send unknown traffic to the internet. Let's look at an example and how we configure this default route. We have our router 1, router 2, and now router 3 with an internet cloud that it connects to. Router 1 has two interfaces configured. One is addressed 192.168.1.1/24 and the other is addressed as 192.168.20.1/24. Router 2 has two interfaces configured. One is addressed 192.168.1.2/24 and the other is addressed 172.32.1.1/24. Router 3 has one interface actually configured as 192.168.20.2/24 and the other interface is internet facing. We know that to send data from router 1 to router 2's 172.32.1.1 interface, we have to complete configuration of set routing options static route 172.32.1.0 / next hop 192.168.1.2. For us to send all other data towards the internet, we can put in a default route by configuring set routing dash options static route 0.0.0.0 / next dash hop 192.168.20.2. Let's have a look at the routing table, the RIB, also known as the routing information base or INET0. So what is the purpose of the RIB? Well, this is where all the learned routes live. It's like a master list of potential paths that a router could use to reach various destinations. What are the sources of these routes? Well, they can come from multiple protocols like OSPF, BGP, RIP, static routes, connected interfaces, etc., etc. Decisions are made here. Junos evaluates all possible routes and chooses the best route per destination. Only the best route, which is based on admin distance, metric and protocol preference, is passed on to the forwarding table. Let's have a look at an example entry in the routing table when we type the command show route. In this example, we're looking for a route that falls within the 192.168.10.0 / 24 subnet. The star before the OSPF means it's the preferred route. Then we see how the route was learned. It was learned through OSPF. It's got a metric of 5 and it states the next hop is 10.1.1.2 via interface GE001. Now, let's have a quick look at the forwarding table. So imagine we've got two warehouse rooms. We've got room A, which is labelled as the routing table or the RIB, and we've got room B labelled as the forwarding table or the FIB. The RIB room will have many shelves and multiple boxes, which we're going to say are labelled with different delivery options. So let's pretend OSPF static BGP. When it's time to send one of those packages, we don't want to spend time looking around. And that's where the forwarding table comes in. It holds only the best delivery routes for each destination, ready to go. Let's have a look at the output of a forwarding table. We use the command show route forwarding dash table. We will see a destination, type, next hop and interface. In Junos, the forwarding table contains one active next hop per destination. You can see it using the command show route forwarding table. Here we see that traffic to 10.0.0.0/24 will go out GE001.0 towards 192.168.1.1. Only the best route is kept, no duplicates, no backups. When a packet arrives at the router, it doesn't check the entire routing table. Instead, it goes straight to the forwarding table to find the quickest path. This makes forwarding fast and efficient. Finally, the forwarding table isn't just in software. It's downloaded to the hardware level called the packet forwarding engine, which we've already mentioned. This means the router can forward packets at high speed without delay. To summarize, the forwarding table is a lean, efficient list of best routes built from the routing table and installed into hardware for fast forwarding. Introduction to routing protocols. Routing without protocols. Here we see 5 routers on our network, but we have not configured any routing protocols on them. Because there are no routing protocols on them, the data packets that we see here have no idea where they need to go to get to their destinations. Routers need help to know where to send packets. Why routing protocols matter. On the top half, we see the no routing protocol and the data packets confused about where their destinations are. In the bottom half, we see the packet knowing exactly the route it has to take to get to its destination because we've added a routing protocol. Static versus dynamic routing. Let's deal with the static routes first. The engineer at his desk has to manually tell the router where to send the traffic. Data needs to get to 172.16.32.1, which resides within the 172.16.32.0 network. So the engineer must configure set routing dash options static route or 172.16.32.0 / next hop 192.168.1.2. Now let's take a look at dynamic routing. We will work with the same network that we had with the static routing. There's no need to configure every path. The protocol figures it out. OSPF is sending a routing update from router B to router A to tell router A dynamically how to get to 172.16.32.0 network. Here we have a look at IGP, which is an interior gateway protocol, versus EGP, which is an exterior gateway protocol. Here we have our 2 cities. We have London and we have Bristol, and we have our road connecting them, or if you like, our cabling. Our cities or our groups of routers, switches, etc. must be within an autonomous system known as an AS. So in this case, our autonomous system number for London will be 100 and for Bristol 200. Our IGP controls routing within networks. Our EBGP controls routing between networks or between ASs. Let's meet the protocols. We have RIP, we have OSPF, we have is, and we have BGP. Hi, I'm RIP. I count hops. I'm simple but not too bright. I don't go past 15 hops. The keywords for me are distance vector. Hello there, I'm OSPF. I use cost and link state info to find the best path. Keywords for me are cost, link state, IGP. Hi, I'm is. I'm kind of like OSPF, but built more for big networks. I use TLVs to scale smoothly. My link words are link state, IGP, TLV, service providers. But as a tip, unlike OSPF, I can support IPv6 natively and scale across large service provider cores. Hi, you can call me BGP. I connect the internet. I use policies and AS paths to make decisions, not speed. My keywords would be an exterior gateway protocol EGP. I'm policy based on the AS path and the internet routing. And here's a pro tip. I'm the only EGP here. I keep peace between autonomous systems. Let's do a quick recap of the protocol, the type, the metric used, and the scope. Firstly, we have RIP, distance vector, metric used is hop count, and the scope is small ID networks. Next, we have OSPF. It is link state, the metric used is cost, and the scope enterprise IGP. Next, we have is. It's also link state. The metric uses a cost via its TLVs, and the scope is large IGP ISP. And we have BGP, which is path vector. The metric used is policy AS path, and the scope is Internet EGP. Here we have the route preference leaderboard. Let's take a look. In first place, we have OSPF with a preference of 10. In second place, we have is with a preference of 15. In third place, we have RIP with a preference of 100. And bringing up the rear, we have none other than BGP with a preference of 170. That's 170. We must remember that in Junos, routing protocols are ranked by preference, and lower is better. RIP, or Routing Information Protocol Overview. RIP, or Routing Information Protocol, is one of the oldest and simplest routing protocols. RIP, Routing Information Protocol Overview. Here we have a laptop and our server with 3 routers in between labelled as router 1, router 2 and router 3 with a hop count associated with each one. If we send a packet of data from our laptop to our server, we know that RIP uses hop count as its metric, so each router the packet passes is 1 hop. Here we see our laptop and our server with our routers noted as hop count 14, 15 and 16. Let's see what happens when our data packet tries to move between the laptop and the server now. The maximum hop limit in RIP is 15. Anything further is unreachable, so our packet will move between 13 to 14, 14 to 15, but then it will drop the packet. RIP, or Routing Information Protocol, is one of the oldest and simplest routing protocols. It's a distance vector protocol, meaning it knows only the direction and distance to a network measured in hops, as we've seen. Each router between the source and destination counts as 1 hop. The maximum in RIP is 15 hops. Anything beyond that is unreachable. One major drawback is the count to infinity problem, where failed routes keep looping, increasing hop counts until they reach 16, at which point they're dropped. RIP is easy to configure, but its limitations make it unsuitable for large modern networks. OSPF Deep Dive. If RIP is the old map book, OSPF is the real-time GPS for your network. It's fast, scalable, and always up to date. OSPF, or Open Shortest Path First, the basics. Before we start with the basics, you can learn all about OSPF in great tech detail that is beyond the JNCIA requirements in my series that can be found at the link shown here. Here we see our network where we have two routes available from router A to router H. The routes have different bandwidths available on the links. So let's have a look and see how OSPF will work out which route is the best path. If we use route A, the packet initially goes from router A to router B at a cost of 1. It then goes from router B to router C at a cost of 1, equaling a cost of 2 altogether. It then goes from router C to router D at a cost of 1, equaling a total cost of 3 so far. The final hop is from router D to router H, also at a cost of 1, equaling an actual route total cost of 4. If we use route B, we go from router A to router E first at a cost of 1. We then go from router E to router F at a cost of 10, giving us an overall current cost of 11. We then go from router F to router G at a cost of 1, giving us a current total cost of 12. And finally, we go from router G to router H at a cost of 1, giving us a total overall cost of 13. OSPF is a link state protocol. It uses, as we've seen, cost, which is based on bandwidth, to choose the best path. And it runs an algorithm called Dijkstra's SPF, and that stands for shortest path first. And it calculates, well, the shortest path. This means that OSPF will choose route A from our scenario above, as it will choose the lowest cost path. OSPF Areas. At the centre of every OSPF network is Area 0, the backbone. Other areas connect into the backbone through area border routers, or ABRs. Here, R4 is the ABR between Area 1 and Area 0. Area 2 also connects to the backbone, with R6 acting as the ABR. As we notice above, all traffic between areas must pass through the backbone, Area 0. Let's do a quick summary. OSPF organises networks into areas. Area 0 is the backbone. All inter-area traffic must go via Area 0, and ABRs connect other areas to the backbone. Final recap. OSPF uses areas to scale. Area 0 is always at the core, and ABRs connect the other areas to it. Let's have a look at OSPF router types. I'm a backbone router, the strength of OSPF. Any router in Area 0 keeps the OSPF core running. I'm an ABR, or area border router. I connect Area 0 with other areas, controlling inter-area traffic. I'm just an internal router. All my interfaces stay in one area. I'm the ASBR, or the Autonomous System Boundary Router. I connect OSPF to the outside world, such as BGP, RIP, well, you name it. OSPF Neighbour Discovery. Here we see our two routers labelled as R1 and R2. The first thing router 1 does is it sends a "Hello, I am R1" packet to router 2. Router 2 likewise sends a "Hello, I am R2" to router 1. Each hello packet also contains a router ID known as a RID, an area ID, a hello interval, and a dead interval. Once completed, an OSPF adjacency is established. It is important to note that if hello packets stop arriving, the dead interval timer counts down. Once it hits 0 with no hello packet received, the router will consider the neighbour as down. OSPF, LSAs and database sync. Here we have 3 routers inside Area 0. Routers flood link state advertisements, or LSAs, describing their links. These LSAs are forwarded to every router in the area. Each router stores LSAs in its link state database, or LSDB. All routers in an OSPF area must have identical LSDBs. The SPF algorithm runs on this database to calculate the best route.